We've seen the infinite precision version of the arithmetic coding algorithm, and now we're ready for the real deal, the finite precision algorithm. So we're going to write down the finite precision algorithm, but before we jump right to that, let's think about what went wrong in the infinite precision algorithm, and we'll start to make some modifications to it that will get us most of the way to the finite precision algorithm. So we're going to do that in this video. So remember back to our example here to illustrate. The thing that went wrong with the infinite precision algorithm is that the difference between A and B is getting very, very small. As you're encoding this sequence, as you're subdividing, 2, 2, 1, the 2, 1 chunk, the 2, 1, 0 chunk. If you had a long sequence, something that weren't like trivial length, like 3, if it were more like the length of a file that you're going to encode, then this difference, the height of this interval is going to be getting very, very small, and you won't be able to represent it on your computer. The difference between A and B is going to be too small. So the main idea of what we're going to do to fix that is we're going to rescale things periodically. We're going to blow things back up to get them back to a reasonable magnitude that we can do calculations in that interval. So remember that when we were interpreting this part B of the encoding process, we actually interpreted this in terms of some rescaling operations. So like here, let me go back to our diagram of that. So I unfortunately erased the previous diagram that we drew for these rescalings, but I've redrawn it for our reference. And so we flipped that interval on its side, and for part B of the process, we reinterpreted things in terms of these rescaling operations. If we ended up in the upper half, then we expanded that upper half, and the A and B got moved over here, and so forth. So we had these sort of 3 different sort of rescaling operations. Either you're in the lower half and you emit 0 and you blow things up, or you're in the upper half and you emit 1 and you blow things up again, or you end up sort of in the middle half and you blow things up. You blow up the middle half. And we used those operations in our algorithm here. So this was part B of our encoder. So here's the encoder. We had part A, which was finding the interval from A to B, and then once we had found the interval, we went to part B, which was finding the shortest binary sequence that corresponded to a binary interval contained in A to B. And we used those rescaling operations. So this was the 0 case in the lower half, and the 1 case in the upper half, and this was the split case, the middle half case. So what we're going to do is actually integrate these rescaling operations into the process of finding A and B. So we're going to integrate parts A and B here. We're going to integrate these loops into this for loop right here. So the first thing we're going to do is we're going to take a look at this first while loop, and we're going to actually interleave these operations with the for loop. And so let's do that. So let me write it first. I'm going to move that s equals 0 up to the top. We may as well go ahead and do that. Let me write it first, and then I'll justify what I'm doing. So I'm just going to take this loop right here and indent it. I'm going to just move it into the while loop right here. So in Python sort of notation, that means now that, let me move these guys out. Back out. That's still 0 and 1. And now this for loop is going to contain this while loop. So this is a green guy right here, continues on down. Redraw that. Just like that. So what is this doing? This is saying, hey, if at some point in the process of subdividing, of narrowing down this interval from A to B, it turns out that B is less than a half, in that case we're in case 0, then we can go ahead and emit a 0 and rescale and blow things back up, and then we'll be in good shape for more subdividing. Or if case 1 occurs, if A is greater than a half, then hey, go ahead and emit a 1 and rescale in this way right here. So let's think about why that's a valid thing to do. So let's go back down to this let's go back down to this example. Actually, let's go back up. We can't see it here. Let's go back up to the picture here. So at the first step, so after this first subdivision step, we started out with, in the algorithm, our initial A was down here, and our initial B was up here. And after the first step, our new A is going to be at 0.6, and our new B is going to be at 1 still. So this new A is bigger than a half. It's going to be 0.6. So we know that whatever the final thing ends up being, let me draw it this way. So this over here, whatever the final A, B ends up being, it's going to be contained in this one binary chunk. So we know that the first symbol, the first binary symbol, the first symbol in our encoded sequence is always going to be a 1. So we'd like to go ahead and emit that 1 and rescale things. So we were here, so we're going to blow up this upper half, this 1 chunk. So let's see what that looks like. So is it a valid thing to do, to blow that up first and then keep doing the algorithm? So let's look down here and see why that's the case. So here, so we're in the case that, let me draw different color, blue, that's good. So 0.6 is right here, so that's, let's call it A1 for A after the first step. And our B after the first step is right here. It's 1 still. So this goes, after if we were to do that, what I wrote down in the algorithm, we go ahead and emit a 1, we rescale, A becomes now here, A1 is here, B1 is still here. So what makes it valid is that it's the same thing to rescale in this way right here, this blowing up this 1 chunk, and then subdivide. So rescaling and subdividing is exactly the same as subdividing this to get the new AB, and then rescaling. So these two operations of rescaling and subdividing commute. They can be interchanged. You're going to get the same AB here in either case. So that's why we can interleave these operations right here with these operations. So we can do these sort of, we don't have to wait to the end to do all these, right? Because if A is greater than half, like in that case above, then we know we can go ahead and emit that 1, and we can go ahead and do that rescaling. And it's not going to affect the A's and B's that come later on. Well, I mean, you're going to have different A's and B's, but it's not going to affect the sequence that you end up emitting. And the reason is because even though you might have a different A and B at a given step in the process of emitting these guys, if one of these conditions applies for the current A and B, you haven't figured out the final A and B yet, but if one of these steps applies for the current A and B, then it will also apply for the final A and B, because the final A and B, the final interval, is always going to be contained in the current interval, whatever it is, AI, BI. Okay, so let me write down those two things that I just said to justify this. So the first one is that, the first point is that rescaling commutes. That's how mathematicians say things. Commutes with subdivision. And by that, I mean, if you rescale in one of these ways, and then subdivide and choose a new A and B, choose a sub A and B, that's the same as subdividing and then rescaling in one of these two ways. So geometrically, we saw that was kind of clear from the picture below. And algebraically, if you algebraically, you can check that. Do this and then this, and then check that that's the same as this and then this. And likewise for the others. So this is the first thing that is needed to justify this. And the second thing is that if, so this is case 0 here, and this is case 1, labeled 0 and 1. If 0 or 1, 0 or 1 applies for the current A and B, for current A and B, A, B, then it also applies, for the final A and B. A and B. And again, that's just because the final A interval from A to B is always contained in the current interval from A to B. All right. So this algorithm is just, it does the same thing as the other one. Okay, now, so this is pretty nice. So this is looking good. This is better because, now if we end up, if A and B happen to be in the upper half or the lower half, then we can go ahead and rescale, blow things back up, and get the difference back to a reasonable size. So that's nice, but there's a subtle issue that still remains. So think about the following case. So there's a pathological case that could still occur. So think about what would happen if, let me draw a line here, new example. Say this is your interval here, and your A and B are like, and let me draw it similar to before. So say you're like here, and A and B are getting very close to the midpoint, right? So you're not, so this is 0, this is 1, this is the lower half, this is the upper half. And your A and B are getting very close. So this is A here, this is B, and so they're not very close right now, but so if you're in a case like, if you're in a case like this right here, then you're not in case 0 or case 1, right? A to B, the interval from A to B is not contained in the lower half or the upper half. So our rescaling operations don't apply. So unfortunately, we can't rescale. And then maybe at the next step, maybe they get even closer to the midpoint, like this. This is your next, so this will be like A1, B1. And maybe, so that's, let me do it this way, A1, B1. And then maybe at the next step, A2, B2 is even closer, B2, and then even closer, and A is always staying less than a half, and B is always staying bigger than a half, and they're getting very, very close. So this is a pathological case which will happen if you have long, if you're encoding a long sequence. It's Murphy's law. It's gonna happen probably. So we need to be able to handle this. And fortunately, we have a sort of rescaling operation that can handle sort of this kind of situation. So remember, this rescaling operation right here, where we blew up the middle half. So that is looking pretty good for this kind of situation, right? What if we could somehow, blow up this middle half? Then A to B would still be contained in the blown up version. So let's go back up just briefly to indicate what's going to happen. So what would happen? Let's think. What would happen if we tried to move this loop here, which was doing that middle rescaling? A is bigger than a quarter, B is less than 3/4. We're in the middle, and we blow up the middle. What would happen if we tried to move this into that for loop? So let's think about what would happen. Let's go down here and draw a picture. Let's draw the picture. All right. So let me get a new example. So let's draw two cases. So first, so let's say here we have, make that a little bigger. So this is our interval, our current interval, and let's say that A and B, let me divide this here into quarters. So this is 0, this is 1. And let's say that A and B are somewhere around here and I don't know, here. So this is A. Switch colors. A and B. Let me actually go ahead and let's divide this into eighths. So now we have eighths. So 0.25, 0.75. So we're not in either case 0 because, A is less than half, B is bigger than a half. But we are in that middle rescaling case. So let's see what would happen if we went ahead and just did that. So here's our new thing. This came from here. This came from here. Oh, that's a squiggly line. And the middle stays where it is. And A and B, what happens to A and B? A goes around here. And B goes somewhere around here. And the quarter, or the our new quarter and 3/4 correspond to these points. All right. And now A is still bigger than a quarter. This is a quarter in our new interval, and this is in our rescaled interval. This is 3/4 in our rescaled interval. B is less than that. So we still have to do yet another one of these middle rescaling operations. So let's do that. Let's draw that. So we're going to have, again, the middle stays, the midpoint stays put. This comes from here. This comes from here. Where does A go? A goes somewhere around here. B goes somewhere around here. And let's draw our quarters now. So this is quarters. Quarter and 3/4. And this is A. This is B. So that's A, B, after one rescaling, A and B after yet another rescaling. So if we had at some point in the process, if we had this A and B, then, so back up here to the algorithm. So if this loop were in here, right here, then, and at this point in the algorithm, we were in that case with the A and B that I drew, we would have done those rescalings that I just drew, but then this does not apply anymore because A, in that last picture, A was less than a quarter. So we would go back up, we would do the next round of the for loop, and we would get a new A and B. So let's suppose that the new A and B, after that subdivision step, let's maybe do them in purple. After that subdivision step, let's suppose that we get, say, let's put it here. So let's say we get this, I'll call it A prime to distinguish, and maybe B is here. So now the key thing is that B is less than a half now on that next iteration through the for loop. And so we now are in the case where B prime, our new B, is less than a half. So we're in the 0 case, right? So we can go ahead and do that 0 type of rescaling. We can blow up the lower half. So let's do that. So this comes from here. This comes from here. And our new A and B, well, let me put the half in. Half comes from right there. B goes to just below half. It's our new, or rather A, and B goes to somewhere up here. All right. Now, before, what we would have done in the 0 case was, this is the lower half down here. We would have emitted at 0 at this point. We would have said, oh, okay, we're doing the 0 type of rescaling, emit 0. Let me put that in green like before. Emit 0. But now we can't just emit a 0 because we did all this other crazy stuff in between. So what are we going to do? What should we emit? Well, let's think about in the following way. Let's think about what if we had, in the previous, in the earlier in the video, the version of the algorithm, actually as I have it written here, without moving this in, what would we have done? Well, we would have gone ahead, at this point, instead of doing these kind of middle rescalings, we would have just done the next iteration. We would have gotten a prime and b prime, and we would have done that 0 case. And then we would have done some other stuff. And let's see what would have happened so we can figure out what we should emit here. So this is, let me move it a little closer. This is what would have happened in the alternate reality. So draw the same picture here. A and B are, A is here, or it's roughly there, B is roughly there. And our new A and B would have been where? Well, let's see, this A prime would have come from here. That would have been A prime, that would have been B prime. And so they would have been somewhere in this little guy right here, A prime, B prime. So A prime would have been right there, and B prime would have been here. So let's go through the steps of what would have happened in the alternate reality world, where we had the previous version of the algorithm without middle rescaling. So b prime is less than a half. This is 1/2 right here. So we're in case 0. So we blow up the lower half. So I'll do this in purple. Actually, we need half. Half. Let's see, 3/4. So this is going to go, hopefully I can do this to scale, closely enough to scale that it works. That's B. Maybe a little closer. A goes here. And then the next step I'll go ahead and draw the last one too. Then we're A prime is greater than a half, so we do this. Then they go here. This is here. It's about here. So that's A prime, B prime, A prime, A prime, prime, B prime. And now, so this is half. And now we're yet again in the upper half, so we're going to go this one, this one. A prime goes around, well, that should go here. Should go about here, if I had done this correctly. This should go around here. A prime, B prime. So it's exactly the same. So here, this is our half. So the A prime and B prime that we get are going to be exactly the same if we did these two middle rescalings and then this lower rescaling, as if we had first done, a new subdivision step and then done the normal sort of rescaling. So let's write down what we would have emitted here. We would have said, okay, we're in case 0, emit 0. Let me do green. This is our 0, 1 since we're in the upper half, another 1 since we're in the upper half again, and then we're split down the middle, so we aren't going to emit anything yet. So what we should have done here, or what we ought to do, is emit 0, 1, 1. So emit at this point, what we ought to do when we hit this case is emit 0, 1, 1 in order to get the same result as if we had done the normal thing. And so if you think about it here, so here's another way to interpret that. Let me label these eighths in the following way. 0, 0, 0, 0, 0, 1, just the normal binary thing. 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And 0, 1, 1 is the interval, is the little chunk that A prime B prime is in. And that's exactly what we should emit. So in general, what's going to happen is that when we're in the case that A is bigger than a quarter, B is less than 3/4, and they straddle a half, we do these sort of middle rescaling things a certain number of times, and then we're going to either end up in the sort of 0, 1, 1 case, just below a half, or the 1, 0, 0 case. But the number of ones, it's going to be 0 and some number of ones, depending on the number of times that we do the middle rescaling. Or it'll be 1, and the number of zeros depends on the number of times we do the rescaling. And we can actually see right away that the number of times, or maybe if you don't see, if you think about it a little bit, the number of ones that we emit, in this case, well, it was just exactly the number of times that we did that rescaling. So we could just count. We could keep a counter. We'll use our S counter that we already have. And every time we do one of these, we just increment it. And then here, we emit 0 and S ones. So when we hit one of our normal 0 cases, we emit 0 and S ones. And if you think about it, what the appropriate thing to do, if A prime and B prime had instead ended up over here, above, with A prime above a half, then we would have emitted 1 and S zeros. So let's put that into the algorithm. So let's do that. So let me go ahead and modify this. I'll do some cutting and pasting here to make it exactly what I just said. So I'm going to put this in here. Actually, I need to leave a little space. A little bit more, maybe. And we need to modify our case 0 and 1 to handle the fact that we have to emit 0 and S ones and 1 or 1 and S zeros. So 0, or rather S started out as 0, and that's good. When we hit this, we increment it like we said we ought to do, and then we just have to change these cases right here. So let me just see if I can do this. Oops. Okay. This is my okay, let me just do it in pieces. Try to do this quickly. I need to make a little bit more space for each of these. Put this down. Cut. Paste. And what we're going to do now is we're just going to modify these emissions right here to account for the fact that we had those ones. So let's see. So in this if loop right here, or in this if case, so this is all of this is going to happen now. Emit a bunch of ones, so it's going to be S ones. And then we need to set S back to 0. Then we're back in our normal sort of state. And in this case, if A is bigger than a half, this is case 1, emit 1 and S zeros. So I'll just denote it this way, S zeros. And again, set S back to 0. And I need to make this, modify these loops to contain the appropriate, indicate the appropriate nesting structure. So this guy now holds all of that, and this guy holds all of that. All right, and now things are looking pretty darn good, because these conditions here, these 0, 1, and S conditions, by doing these rescaling operations, we guarantee that the difference between A and B at any given iteration of the loop, when we get back up to the top of the loop, the difference between A and B is always going to be at least a quarter. And that is nice, because that means that that we're not going to, A and B are not going to be getting very, very close together. So things are looking pretty good for our rescaling and in terms of um, of not running out of precision. Now there's still some work to go to make to actually turn this into a finite precision algorithm. The encoder, this is pretty close to the encoder, but the decoder, we're going to have some work to do to make the decoder in the finite precision case work, because you need to do the same rescaling operations at exactly the same times in the decoder, because you're going to be rounding off. And so you're going to need to do these same rescaling operations at the same times. That's the key during the decoder as during the encoder. So we'll see that when we look at the decoder. That'll be coming up soon. And one other thing that we're going to need to change about the encoder is we're going to, rather than use, so here we were using like arbitrary real numbers. We're going to, rather than use something like floating point where we don't really know what's going on, we're going to use integers, and we're going to explicitly handle any rounding that occurs so we know exactly what's going on. But these rescaling things that we did here, integrating this into interleaving these with the subdivision steps, this is a key part of the algorithm. And so hopefully by going through this first in the infinite precision case, it will make it more comprehensible to you next when we look at the finite precision algorithm.